In this video, we're going to take a look at single displacement reactions. So we're going to be able to identify single displacement reactions and also predict the products of single displacement reactions. Remember from grade 10 that a single displacement reaction is where you have a single lonely element reacting with a compound, and that element will kick out one of the elements in the compound and become part of that compound. So for example, A kicks B out, A is now part of the compound, and now B is alone. So at the end of the day, we have a single lonely element here. As you can see here, we have zinc reacting with hydrochloric acid. The zinc is alone, it kicks the H out, and we have zinc chloride as a new compound, and then H2 as our single lonely element there at the end. So that's called a single displacement reaction. And so in grade 10, you basically learn that every time you see a single displacement reaction, you can assume that you're just switching spots. But that's not always the case. Oftentimes what you're going to see is you have to use a table, an activity series table. It's a list of metals in order of reactivity when it comes to single displacement reactions. And to predict the product, you have to take a look at where the two elements lie in this list. Anything higher up can kick out anything lower on the list. So this is one of the activity series you can use when you're doing assessments, but there's one activity series over here in your data tables that you have included on your unit calendars that you can use as well. It's a nice and simple one. It's listed right over here. Activity series for metals and then for non-metals. So we're going to take a look at examples first with metal single displacements and then afterwards for non-metal single displacements. So we're going to go ahead and take a look at several types of single displacements. We'll do metals reacting with acid or water, and we'll see how we can predict that. And so we can see some examples here. We're going to take a look at metals reacting with ionic compounds that contain a metal in them. So I just call this metallic compounds here. And then afterwards, we'll do a few examples where we have non-metals displacing non-metals as well. And throughout this presentation, I want you to notice that there are some little scenario predict, observe, explain problems. And so what you'll do is you'll watch these scenarios, these demonstrations, and you'll answer the question. So you'll start off with a little prediction, will a reaction occur? Write out a balanced equation and classify the type. And then afterwards, you're going to watch the demonstration, see if a reaction occurred like you predicted, and then describe the evidence that a reaction occurred if it did at all. And so this is your scenario given there. And you have a few of these for the different types of reactions to try out. So let's go to our handout and try some different examples. So here we have our single displacement reaction already defined for us. We're going to start off with some examples of single displacement where we have metal reacting with acid and water. So if you have a metal reacting with an acid, what's going to happen is you're going to produce an ionic compound called a salt and hydrogen gas, providing that the metal can actually kick out the H from the acid. So let's take a look at an example. Here we have zinc reacting with hydrochloric acid. We need to take a look at our reactivity series to see if zinc is above H in it. So let's go to our data table that we had over here. Let's find H. So here's H, and zinc is over here. So zinc is more reactive than H, which means a reaction will happen. We can also look at the reactivity series table over here. So for example, if you look, we have hydrogen here, zinc up here. So zinc will be able to displace hydrogen in a single displacement reaction. So let's go ahead and try that out. So I'm going to make my little arrow here. Notice the zinc is solid at first and the acid is aqueous, and that's usually how it starts off. We'll put them together and the zinc will kick the H out. And so what's going to happen is we're going to get H alone, but as its Hofbrinkel version. So hydrogen gas, as you can see here. And then we're going to have a crisscross between the zinc and the chlorine, which is ZnCl2. And generally, we'll put aqueous for now, but I'll teach you how to figure that out later on. We use a chart called a solubility chart to figure out if it's soluble or not. But for the most part, starting off, we're going to put aqueous. But later on, like I said, there will be a chart to figure that out. So we can go ahead and try the next example. We have copper reacting with an acid, so metal reacting with an acid again. and we're going to see if it's going to produce this. So we're going to predict our products. By the way, just to mention, I didn't go ahead and balance this yet. You can go and try it yourself. So for example, well, I'll do it. May as well. It's pretty quick. So put a 2 there. That gives us 2 H's, 2 Cl's, and then the rest is all balanced. So we have to look if copper is above H in the reactivity series. So if we look over here, we have hydrogen, and copper is below it. So copper is below H. And let's go look at our other data table over here. Here's H and copper is below it. So because copper is below H, copper will not be able to displace hydrogen. So we would say that there is no reaction. Or you could put NR for no reaction, because copper is not reactive enough to kick the H out. So now let's try an example with water. So when we do an example with water, what I like to do is I like to think of water as HOH. So and then that's still liquid here. So you're going to see if copper can kick out one of the H's, not both. But as we saw in our reactivity series, copper is not more reactive than hydrogen, so it can't do that. So this one here is going to be a no reaction as well. Let's go take a look at this one here. Na plus water, so I'm going to write it as HOH, liquid there. And we have to go see if Na is higher than H in our reactivity series. Na is way over here, and H is down here. So Na wins, it's able to knock H out. So Na will kick one of the H's out, and the H will be alone. So we'll have a hydrogen gas produced, plus now the Na is with an OH. And so all you have to do is the crisscross between the metal and the OH. And so we get Na, OH. And that will be aqueous because it's a base. So what we just saw here is that when you have a metal and water, it'll produce a base and hydrogen gas. So essentially, any metal that's above hydrogen in the reactivity series is going to displace hydrogen to form a hydrogen gas from the acid, or from water to form hydrogen gas. And sometimes, in some cases, in order for the reaction actually to happen, you might have to put heat into it to make sure it happens. Even if it's more reactive, you'll have to heat it up a little bit to make sure that it actually takes place. Just to show you that on your periodic table. So we also have a reactivity series list provided in this periodic table here. And so here it is. And so if you actually take a look at this list here, this is sort of an extension part to it. Some elements will be able to displace hydrogen from cold water, but then a whole bunch need water that's warmed up. And a whole bunch of elements can displace hydrogen from acids, but nothing down here, for example. So here you can see that some can do it from cold water or hot water, but others will need the water heated up even though they're above hydrogen. So that's just something to mention. For the most part, though, we'll assume that the water's at a high enough temperature to allow that displacement to happen, providing that we're above hydrogen in our single displacement chart. So that was just two examples of single displacements with metals and acid, metals and water. And now we'll take a look at an example of metals with just straight up ionic compounds called metallic compounds, or just they're salts really. So we'll have a metal reacting with an ionic compound that has a metal and nonmetal. Metal A will kick the metal out from the metallic compound, and we'll have metal B alone, and then we'll have a new metallic compound. So again, the metal can only displace if it's higher up in our reactivity series list. So let's go take a look over here. Magnesium reacting with zinc iodide. We're going to see if magnesium can kick out zinc. We can use the reactivity series list on our previous slide. I'm just going to use the one down here. So zinc is over here. Magnesium is over here. Magnesium is higher up. So because magnesium is higher up, we're able to kick it out. So zinc is now going to be alone as a solid. And then we'll have magnesium iodide. And for now, we'll put aqueous, but later on I'll teach you a way to figure out if this is actually aqueous or not. So next we need to take a look at nickel reacting with zinc iodide. Oh, and by the way, the magnesium iodide here was determined by the crisscross between magnesium and iodine. So +2, -1, crisscross it, and you get that. And then you need to make sure it's balanced, of course, and it looks balanced to me. So now we have to compare nickel and zinc. Here's nickel, here's zinc. Zinc is higher up, so this won't happen. Nickel will not kick zinc out because it's not more reactive, so we get no reaction here. So it's the same principle, except we're not dealing with acids and water. We're dealing with a metal, displacing a metal from an ionic compound that has a metal in it. So this is your reactivity series list. One interesting thing that some students sometimes notice is that lithium is above potassium in the reactivity series list, and we had learned that the metals become more reactive as you go down a group, so potassium should be more reactive theoretically. But now these reactions, they actually happen in solution. And in solution, lithium is just able to displace potassium. It might not be more violent than potassium in water, but it's able to form compounds more effectively in solution compared to potassium, primarily because of its size and the size of the ion that forms. You don't need to know much more than that, but it is true that lithium in these type of single displacement reactions in aqueous solutions will be able to displace potassium from the list or from a reaction. And so you'll see that reflected also in the other data tables area over here. So in this video, what did we see? We saw what single displacements are. We saw that you can have metals reacting with acid or water and kicking out the H if they're above the H, and they produce hydrogen gas in that case. We saw metals reacting with compounds that contain a metal, and so essentially the metal would kick out the metal if it's higher up on the reactivity series. And what we'll do next is we're going to take a quick look at this once again. So you want to make a prediction to see if a reaction will happen based on that scenario that's provided. And so what you're going to do is you're going to try to write out a word equation first. And after you write out that word equation, what you want to do is predict what the products could be if the products are formed. You might want to look at your reactivity series to see if copper, for example, can kick silver out from silver nitrate. And if you think it can, then write a balanced equation to illustrate that and watch a demonstration to see if it actually happens and to confirm if your hypothesis was supported or not supported, was correct or not correct, essentially. So in the next video, we're going to take a look at single displacement reactions where nonmetals replace nonmetals.